Hi there, we're Team Red Sox from BU Spring 2014 EC551 course. We're here to present you an overview and demo of our course project entitled the 3D Motion Controller. Our concept is simple. First, rig an FPGA with sensors. Then, crunch some numbers. Finally, realistically render an image and its transitions on screen. The motivation for our project stems from the idea that gesture-based control combined with 3D rendering has many cool and useful applications. A few examples are architectural modeling, remote control for surgeons, immersive video games, and image stitching. Our project contains 3 functional elements. First, interfacing with the gyroscope and accelerometer to accurately capture 3-axis angular velocity and acceleration. Second, creating a 2D maze game with the cursor controlled by the sensor board. Third, rendering a simple wireframe cube with movements on screen accurately depicting movement at the sensor board. Since our project is divided into 3 functional demos, we decided to combine demos 1 and 2 into one design, with the third demo on its own design. Design 1 contains the SPI interfaces of the gyroscope and accelerometer, feeding inputs to our orientation calculation module. With this sensor data, we perform calculations for the rocking ball demo and maze and output to the VGA by means of the VGA driver. A hardware switch selects which demo to display to screen. Our second design contains the same modules as the first, with the exception that the previous demo modules are replaced with the wireframe cube demo module, which houses the logic for the third demo. Here's our first demo. Our first demo demonstrates our ability to interface with the gyro and accelerometer through the SPI interface protocol. The first part of the demo is a cursor which moves according to accelerometer input. The second is a ball on line animation. Here's a snippet of code for the demo. As you can see, for the accelerometer, we instantiate the SPI interface module as well as a master module to control the interface, and similarly for the gyroscope. So here we have our sensors interfacing. We have gyro and accelerometer, and basically we have the first demo, which is a ball and line animation. And once I switch this on, you can see that it's balancing on the line. There is the gyroscope feeding us data, and that's how we keep track of angle of the line. And the second half of the demo is a cursor that we keep track of by that switch. So we just switched over to, now we're interfacing with the accelerometer, and you can see the movement of the board generates movement on the screen of that cursor. So you can see it's tilting right, now moving right, up, and back down. So, and this serves as the basis for the other 2 demos, which is the maze and also the wireframe cube.
The aim of the game is to maneuver a ball through the 2D maze. For this, the gyro takes in data from the user, and this data is converted to the dimensions of the ball that will move through the maze. Collision detection algorithm is implemented throughout the maze. A toggle switch is a salient feature of this game, because when the switch is turned on, the maze blinks and different portions get displayed. This makes it tougher for the ball to complete the game. This slide shows the block diagram of the concept. As is seen, the top module has 3 parts. Number 1, the data select takes the input from the gyro and the accelerometer and the switch. Number 2, the SPI component converts the data to the dimensions of the ball that can be used for collision detection. Number 3, the task 3 module has 3 sub-modules. The maze portion displays the various portions of the maze. The ball logic and cursor ROM display the ball as a sprite on the maze. The VGA controller displays the entire module on the VGA monitor.
So this is the 2D maze, and as you can see that the ball is moving through the maze, and I'm manipulating the FPGA board to make the ball move through the maze. So up it goes, right, and collision detection has been implemented thoroughly through the maze. Now if I switch on the toggle switch T5, the maze will start blinking, different portions of the maze come out. So this makes it difficult, and you need to memorize portions of the maze to make the ball move through it properly.
In order to render a simple 3D image, we need to be able to draw a line between two arbitrary points on a screen. We also need to be able to display a number of lines at the same time, and then refresh the screen and display a new set of lines. Arbitrary line drawing was implemented using Bresenham's line algorithm. This was one of the first graphics algorithms developed in the field of computer graphics. The basic idea is that you start at one endpoint of the line and work your way to the other, making decisions along the way about which pixels will be illuminated. The algorithm assumes that the slope of the line will be greater than or equal to 0 and less than or equal to 1, in order to reduce your next decision to one of 2 points. To display lines of other slopes, the input line coordinates must first be pre-processed. If you start at this point, you will either move directly to the right or down and to the right. You make this decision based on which pixel is closer to the equation that defines the line. In this case, the pixel directly to the right is closer, so that pixel is illuminated. This process continues from each newly illuminated pixel until the other endpoint is reached and all of the pixels for the entire line have been defined. The Bresenham algorithm was implemented in hardware and then wrapped in a higher level module that controls access to the VGA display buffer. The line drawing hardware handles the process of clearing the display buffer and then loading all of the points that represent the lines out of a set of FIFOs. The display buffer is implemented as a dual-port RAM, with one port connected to the display state machine logic and the other port connected to the VGA display logic. The line drawing component worked well in hardware because of the integer math implementation and the simplicity of the state machine required for the calculations and decisions in the Bresenham algorithm. The design trade-offs for this design were mainly the result of the screen buffer used to store the points output by the Bresenham algorithm. This design implements a 640 by 480 resolution that can only indicate if a pixel is on or off. Because of FPGA space constraints, it was not possible to implement a higher resolution or store different colors for different lines. Some possible alternatives for future implementations would include the use of a larger FPGA device or an off-chip memory to store a screen buffer.
Now, moving on from the Bresenham's calculation, we're able to now take the gyro and accelerometer data and put that together into render a three-dimensional cube. This cube consists of 8 points and 12 lines, and we'll be able to render on screen via the line drawing buffer and be able to simulate rotation through matrix multiplication using the gyro and accelerometer data as input to rotate the cube on screen. Now, for the cube, we have an 8-point cube where our axis of rotation will be dependent on a 4-fold axis rather than a 3- or 2-fold axis. This renders the axis to come out perpendicularly to each face rather than coming out from the edges or from the corners. Now, this is a top-level module outlook of the cube rendering module. The inputs will be gyroscope and accelerometer data. This will be fed into a sine and cosine table, and outputs will be put into the matrix multiplication table. Now we have a separate place where we store the 8 points of the cube. Now this module will output one of 12 lines and it will cycle through that. This is done in order to minimize the amount of calculations that the FPGA chip is able to do. So this is limited again by how much slices that we're able to utilize. The matrix multiplication table is also broken down through 4 different stages, cascading through the calculations of each line in order to break it down so that under each clock cycle we are able to utilize as many slices as we can without going over and overloading the slices. Now the output of each line will be eventually outputted to the line drawing module one at a time into the buffer, and when the buffer is full it will render the cube on screen with the new positions in accordance to the cosine sine of the XYZ. Now this is a code snippet of the matrix multiplication done in order to render the rotating cube. As we split up the calculation into 4 separate cascading states. Each state will be added onto the sum of the previous state. At the end of the 4th state, The result of the new line will be pushed into the display buffer. The sine and cosine inputs from the lookup table will be fed into each step. We needed to break up the calculations into 4 separate steps because the FPGA we are currently using did not have enough slices to handle the entire matrix calculation for all 3 points in one go. Furthermore, when we first went with a single calculation clock cycle design, Xilinx did not catch the timing error, so many hours were spent before we caught the timing error ourselves. Splitting it into 4 clock cycles, we were able to reduce the utilization of the DSP48A1 slices from 100% to 58%. This trade-off meant that our refresh rate of the cube rotation had to slow down in order to accurately calculate the new points.
The complementary filter combines the high-pass gyroscope measurement and the low-pass accelerometer measurement and output orientation data in degree for x, y, and z axes, which will be used as inputs for the wireframe cube. Gyro measures the angular velocity in degree per second. Integration is constantly performed at each sample point in order to obtain the degree value. But this degree value tends to drift over time because the noise is accumulated with degradation. So gyro's reading is only accurate for a short time. This is the reason why we introduced the complementary filter and include accelerometer in the measurements. So on the short term, we use the data from gyroscope because it is very precise and not susceptible to external forces. On the long term, we use the data from accelerometer as it does not drift. On the left, we have the motion sensor L3G4200D using the PMOS gyroscope. It measures the rotational speed, which is the angular velocity of each axis. Looking into the direction of the positive axis, a clockwise rotation will give you a positive reading, whereas an anti-clockwise rotation will give you a negative reading. Note that the angular velocity are transient readings. If the gyroscope were to stop from moving, it will simply show 0. On the right, we have the motion sensor ADXL345 used on the accelerometer. It measures gravity vector of each axis. Note that a measurement reading is always opposite of the gravity. Take the upper view of the 4 positions drawings, for example. Gravity is pointing straight downwards, with y and z plane perpendicular to it. So y and z readings are always 0, whereas x-axis pointing exactly to the opposite direction of the gravity, it has a reading of 1g, not minus 1g. In the case where axes are not parallel or perpendicular to the gravity, measurement readings shows the axis projection onto gravity vector. So if x-axis, for example, were to deviate by 60 degrees from gravity, the reading would show 0.5g. For more information, please refer to the demo code on Digital website. Now let's look at the structure of a complementary filter and how to get the orientation position data in degree. The SPI interface and SPI controller interact with the component and scale the raw data to a user-interpretable readings. At the complementary filter inputs, gyroscope has all 3 axes 16-bit signed angular velocity data, and accelerometer has all 3 axes 10-bit signed gravity projection data. The angular velocity coming from the gyro is integrated over time to get the degree value and constantly added to itself in 2's complement representation. The gravity data coming from the accelerometer are fed to an Arc10 Cortex core and spit out the degree value. The 2 results are combined together with a high-pass gyro and low-pass accelerometer complementary filter. This is simply done by giving a dominating coefficient to the gyro and a small tuning coefficient to the accelerometer. Note the 2 coefficients always sum to 1. The values shown here are for demonstration purpose only. Experiments on different combinations for optimal results.